As we talk about gases, not only will pressure and volume be important, but temperature is going to come into play now. We have not talked about temperature other than the reference to friction doing work would make something warmer. That's the only reference we've made to temperature so far this semester. Now temperature is going to play an important factor because it turns out the actual energy a gas possesses depends upon how many molecules you have, but it also depends upon what the temperature of it is. Turns out there's a direct relationship between the energy of a gas and the temperature of the gas. So if you change the temperature of the gas, that's going to change how much energy it has. Okay? So temperature systems. And I'm not sure if I spelled that correctly. I apologize if I didn't. Good, you guys don't know either. Makes me feel better. Fahrenheit. That's this temperature system we use here in the US. If you watch the news and it says it's supposed to be 100 degrees today, I'm not happy about that. But that's Fahrenheit. The rest of the world uses Celsius. It is easy to convert between the two. If you want a temperature in Fahrenheit, but you have it in Celsius, 32. So T sub C means your temperature in Celsius. You multiply that by 9/5, add 32, and that's not supposed to be a 5. Sorry.
What? Oh man, I committed that to memory.
That's supposed to be an F for Fahrenheit. Yeah, and understandably. Sorry about that. I was getting ahead of myself with the 5 in the equation. Celsius. If you have a temperature in Celsius and you want to, in Fahrenheit, and you want to get it to Celsius, bring the 32 over, multiply by 5/9, and we'll have the temperature in Celsius. Easy to convert between the two. Now, a lot of scientists actually use the Kelvin scale. That's even easier. The temperature in Kelvin is simply the temperature in Celsius plus 273. And if you want to be technical, 273.15. The 273 really is sufficient enough. The Kelvin scale basically is only positive values. With Celsius and Fahrenheit, you can get negative temperatures. 0 is just a reference. It doesn't have an absolute meaning. Other than 0 Celsius is where water freezes. 100 Celsius was where water boils. Kelvin, 0 Celsius is 273 Kelvin. The absolute coldest an object can be is when the temperature in Kelvin is 0. That's called absolute 0. If you could reach absolute 0, all motion would cease to exist. Objects would be perfectly stationary. Now, that's yet to be proven. Nobody's reached 0 Kelvin.
I got that cold one time on a ski trip.
You have icicles hanging out your nose.
Yeah, everything stopped moving. It's not moving.
Okay, so Kelvin, basically, our values are from 0 up. They're only positive. The difference between Celsius and Fahrenheit is just how big the scale is. So water freezes at 0 and boils at 100 in the Celsius scale. In the Fahrenheit scale, it freezes at 32 and boils at 212.
Depending on your altitude.
Yeah.
210 here.
So 0 to 100 versus 32 to 200 and something. It just makes 1 degree mean a little more in Fahrenheit. It just spreads it out over a little larger region, really is all. The equations we're going to use that involve temperature will require our temperatures to be in Kelvin. That's going to be necessary. Unlike converting, say, from inches to meters or kilograms, well, we didn't ever convert from kilograms to slugs, but kilograms to, say, grams and so forth. When you do a problem with temperature, if your temperature needs to be in Kelvin, you must do the conversion prior to plugging the numbers in. You cannot do the conversion after running the equations, and that's because of the fact that you have a plus sign in the conversion. Okay? So just get in the habit of converting it first, and then plugging it into your equations. Okay. Totally bunch of little random little pieces of information. As we talk about energy, we're going to talk about the change of phase of a material. For example, changing ice to liquid water. That's a change of phase. Ice is a solid. Liquid water is obviously a liquid. We could change liquid water to water vapor, and that would be a change of phase as well. So change of phase requires energy. To melt ice, you have to put energy into the system. Energy has to go in to break all the bonds that are holding all the water molecules together. The difference between phases is how easily the molecules bond together. In a solid, when the temperature is low, the molecules don't move very fast because they don't have very much energy. If they're not moving very fast, then they can easily bond with each other. That's what makes up a solid. If you heat the material up, that makes the molecules move faster, and it makes it harder for them to actually bond together. That's why it becomes a liquid. A liquid, the molecules are still interacting with each other, but they're not bound tightly together, and that's what makes it liquid. You keep heating it up, you sever the ties between the molecules, and you get your vapor, or your gas. So we're going to talk about the energy involved in changing phase. Turns out, just as you guys mentioned, water doesn't boil at 212 at this altitude. It doesn't boil at 100 degrees Celsius at this altitude, and that's because the pressure is a bit less than 1 atm at our higher altitude. You can draw a phase change diagram that relates pressure to temperature for materials. This is just a rough sketch, just so you know. To remember which one's which. So for example, for say this pressure and this temperature, our object would be a solid, whatever this material happened to be. But if I keep the same pressure and increase the temperature to some higher value, our object will now become a gas. If I keep the same temperature and increase the pressure, it can be a liquid. So pressure and temperature together determine what phase your material is in. These lines, this line represents sublimation. If you have this exact temperature and this exact pressure right here, you can have both a solid and a gas at the same time. Great example would be dry ice. A chunk of ice turns directly to vapor. We have the right pressure and temperature to make that happen. So sublimation is going from the solid to the gas state. Solid to liquid would be our melting or freezing, just depending upon which way it's going. That line represents, at any particular point on that line, if you have that temperature and that pressure, you could have a solid and a liquid at the same time. And likewise, liquid to gas is what, boiling? or condensing, depending upon which way you're going. So there's certain pressures and temperatures that allow an object to be a solid versus a liquid versus a gas. There is one special point right here. That's called the triple point. At that exact pressure and temperature, you can have all three phases at the same time.
Is that related to supercritical?
I'm not sure. Dry ice bombs.
Yeah.
That's exactly what it is. You're at the triple point. You put dry ice in a sealed container. As it sublimates, the pressure starts to get bigger and bigger and bigger. At some point, you're going to reach this right pressure, and it turns out it works pretty well around room temperature, and you can actually see all three versions at the same time. I don't recommend being up close and personal for very long, because you wouldn't want it to blow up on you and hurt you. For water, the triple point is just, it's like 0.6 ATMs that you have to have. And actually it's 0.06, I think. Ridiculously low pressure and temperature. So we really, without a special laboratory setting, we wouldn't be able to see the triple point for water. Okay, so we're going to talk about energy. To go from a solid to a liquid requires energy. You somehow have to put energy into the system to take a solid and turn it into a liquid. What about going from a liquid to a solid? You need to take the energy out. Exactly right. Likewise here, if you want to go from liquid to a gas, you need to put energy in. To go from a gas to a liquid, you need to take energy out. So we'll talk about the energy exchanges in these situations. Questions so far?